Hello all, my name is Amit Sharma. Today we are going to discuss about the frequency reconfigurability property of graphene terahertz antenna. As we can see in the screen, there is a circular shaped, circularly polarized graphene terahertz antenna where the substrate used is silica, the bottom is of PEC ground material, the, the patch is made up of graphene. Here, to achieve frequency reconfigurability, the chemical potential of graphene is varied. So we see here uh, in the parametric sweep, we can add a new sequence, and in the sequence I have taken a parameter which is graphene chemical potential. Here I have varied the graphene chemical potential from 1 to 1.5 and then 2 electron volts. So I have simulated this task, and the result in terms of S11 are presented here. We can see that the green plot of S11 shows the chemical potential of 1 electron volt, while the red one shows the 1.5 electron volt of chemical potential, and the blue plot shows the 2 electron volt of chemical potential. So we see that the variation of chemical potential is shifting the S11 response towards right side while improving the S11 characteristics. This is what we call frequency reconfigurability achieved by graphene terahertz patch antenna at terahertz frequency. We see that at 1.5 electron volt, the S11 response is way better than at 1 electron. So to achieve this frequency reconfigurability, we vary the chemical potential, which indirectly vary the conductivity of graphene. So with the variation of conductivity of graphene, the change in the S11 plot is achieved. Now we can see the variation of circular polarization or axial ratio with the variation of chemical potential. So here the plot is for axial ratio. We see that for each value of chemical potential variation, we have the varied or we can say different axial ratio plot. This one is for 1.5 electron volt. For 1 electron volt, the plot is like this, and 2 electron volt, the plot is like this. So this is the verification. This variation in axial ratio plot, the variation in S11 plot with respect to the chemical potential, this verifies that the patch of made up of graphene is acting like a proper graphene. Then only we get the chemical potential variation outcome in terms of variable S11 response. Otherwise, if the, the prepared graphene patch is not proper, then we don't get the chemical potential response, variation response in terms of S11 variation. Here, one thing is important that we cannot vary the chemical potential to 3 electron volt, 4 electron volt, 5 electron volt. I mean, there is a mechanism involved with this. So we can take a reference, as I have earlier expressed, the work from Sasmita Das ma'am and Patnaik sir, performance enhancement of graphene plasmonic nanoantennas for terahertz communication. So in this work, they have expressed or they have shown a relation. We can see here in the table 1 that Vg is the gate voltage. How here this is the gate voltage. We can see this in this figure. The applied gate voltage between the graphene and the silicon vary the chemical potential in for graphene. So by applying the gate voltage of 7.6 volt, the achieved value of chemical potential in electron volt is 0.3 electron volt. While while we can see that increasing the gate voltage to 13.6 volts gives us zero point 0.4 electron volt, and for 30.6 volts of gate voltage, the electron chemical potential is 0.6 electron volts. We see that very high value of gate voltage is required to achieve just zero point 0.6 electron volt of chemical potential. So for apply 2 electron volt of chemical potential or 4 electron volt of chemical potential, we may need or we may require 100 or 150 volts of gate voltage. So for smaller micrometer size structures uh, of graphene antennas, applying a gate voltage of hundreds of volts may damage the structure. So it is always advisable to use smaller values of gate voltage, and hence to use the smaller values of chemical potential to tune the graphene terahertz plasmonic antenna. The other things about the antenna, graphene antenna, uh, is its feeding. So we can see here I have used a discrete port to feed this structure. Uh, when we go to ports here, so it is visible. You can see that a discrete port from ground to patch of the antenna is connecting and supplying the patch. So this is how we are getting the excitation and the response for two layer 2D response specifically. You can see here in terms of electric field distribution. So we see that the antenna is getting properly excited. So this is how antenna testing for terahertz antennas, graphene terahertz antennas is done. The gain of this antenna at 1 terahertz is quite significant, 3.36 dBi, with the efficiency of 70% radiation efficiency and 50% total efficiency. Yeah, it is uh, famous for graphene terahertz antennas that they don't provide a sufficient efficiencies. As we can see it here, the total efficiency is around 50%. So a lot of research is going on to improve the performance in terms of efficiency of graphene terahertz antennas. Thank you.